All right, so what do people want to do? There's lab 6 and there's lab 7.
Lab 6 was due on Friday?
Due on Friday, right? Yeah. Are there any questions on lab 6?
How about number 10?
10 on lab 6?
Yeah.
Flat. Yeah, let's look at that. Look at what I'm doing. I'm starting with a hello program. I didn't even read the exercise yet. All right, that's a good starting point. I still see people not starting here. Of course, that's up to you. You can carry on and do it that way. But I'm just going to keep repeating my, I guess, my opinion about that. I think it's better to have a running shell and work within that and go through a sequence of steps. And in each step, you have a compilable, runnable program. And at the very last step, you've got the solution. All right, here's the function, and we're going to need, all these questions are similar. We need to implement this function. Let's take a look at this. There's the function. It returns a vector. I see it returns a vector. So look, I know, without even reading, of course I wrote the problem, but without reading, you should see right off the bat, you don't have to read any more. You say, well, I have to return a vector. Well, I got to make a vector. See, I'm getting oriented to the problem like this. So let's create a vector v, and then we're going to do stuff, and then we're going to return v. And that's what the function looks like. I can just see that without knowing what Flatten is supposed to do. It has to return a vector. And so we need to create the vector and then return it. Okay. Write a function named Flatten that takes, oh, you know what? We got to check to see if it still compiles. And it does. Why does that compile? Maybe because I didn't save it. There's the problem. A vector is undefined. So we need an include directive for the vector header. There we go. So now that compiles. There we go. Write a function named Flatten that takes a two-dimensional array of integers with 100 rows and 200 columns and returns a vector that contains all of the array's elements. Copy the values a row at a time. In other words, first copy row 0 into the vector, then row 1, then row 2, and so on. The declaration is given above. So we need to flatten out a two-dimensional array. Here it is. So we have 100 rows and 200 columns. So first we're going to add into this vector v. We're going to call pushback. We're going to call pushback over and over again. Well, we're going to be picking out elements from A. And it'll be by row and column. I'll use R and C for that. And so R needs to range from 0 to 99, and C, and for each value that R takes on, C has to range from 0 to 199. We use a for loop for that. So there is a loop that has range, that has R starting at 0 and incrementing until it hits 100 and then stops. So we don't execute the body of the loop when R is 100, but we execute the body of the loop when R is 99. And when you see this here, you know that the array has indices from 0 to 99, not 100. 100 is not a valid index. That's the size of the array. Because counting starts at 0, the last valid index is 99. And now, for each value of R, see, we're indenting here. You see that? So inside this body of this outer for loop, R has some value, whatever R is. And for that value of R, we're going to loop. We're going to create a loop that has C range from 0 to 200. And it exits when C hits 200. And this is what we do right here. Whoops. We have an R and a C, and we push that onto V. Then return V. So that's the function. So I might give that problem on exam 3. So I might ask you to do this. And this is all you would do. All you would have to do for that problem would be to provide that code right there. But we're going to go a little bit more because this is a lab exercise. So I'm going to add some test code.
So, but in the actual exercise, it's not, that's all that the exercise
This is good enough,
asking for,
yeah.
right? Okay.
In the exercise, I should have said to put test code in there, but I didn't. Here, like 8, write test code.
Yeah.
And 7, I don't say anything. Right? So I should modify those to have you put test code in there. All right. So let's look at the test code. Well, it's hard to do test code for this because the array is so large. But basically, we'll use the same loop structure to populate an array. So this is not sure what we would put in there. We could put in there, let's do this. Let's put in R times 200 plus C. So that means the two-dimensional array will have, 0 through 99 in the first row, 100 to 199 in the second row, and so on. No. It'll be in the columns, right? Is that right? It would go through columns. So we would have 0 through 99 in the first column because it's 100 rows. There's a column has 100 elements. Is that right?
You'd want that to be R times 100, not 200.
Say it again.
It should go by row, and then that should be R times 100 if you want it to.
R times 100?
0 through 99.
Yeah, maybe that's right. Let me think. Column.
Would go 0 through 99 for the first column because
Yeah, that's right.
0 times.
That's right. That's right. Is that right? Is this going to work? I can't think about this.
It'll assign something.
Yeah, what's it going to look like? So when R is 0 and C is 0, then this calculation is 0. So it just gets a 0. And then we increment C by 1, and then this calculation gives us 1, like that. So the first row will look like that. And to 99, right?
199.
Well, wait a minute. But this goes 200 times.
Yeah. So to 199.
So this, but there's only, that's right, there's 200 columns, so it's 199. That's right. That's what it looks like. So this will work, won't it? I think it'll work.
You got it right the first time.
And then when R becomes 1, then it's 100 plus C, and C is set back to 0. So it'll be 100 here. So don't we want to use 200?
Yeah.
So we want to use 200 here. And then the next one is 201. 202. There we go. It's 203. And this is 399. And this keeps going. And then we have the last row, which is 99. 99 times 200. What's that? So 99 times 200 is, I'm gonna figure that one out. 299, so what's 200 hundreds take away 200? What's 200 hundreds? 200 hundreds. Take away 200. So that's like,
19,800.
Yeah.
like that.
And put a 19 in front of it.
Oh, 19. So the numbers are getting big, right? And that's going to hit, how big does it go?
19,999.
It's going to go to that minus 1.
So 19,900.
Did I do that right?
What it should be.
Is that right?
Well, the very last one is
How many elements are there in a 100 by 200 array? It's 20,000, right? 20,000. So if we start at 0, if we started at 1, we'd hit 20,000. But we're starting at 0, so we're going to hit 1 less than 20,000. So let's see if that works. So, and then we call flatten. So vector of int v we're going to flatten a. Well, we need to declare a. So a is 100, 200. See, when we declare a like this, when it's an int, you know, it allocates space, these 20,000 positions, 20,000 slots get allocated, but their contents are uninitialized, so you don't know what's in there. It grabs available memory from the memory pool, but there's no guarantee what that memory will be initialized to. And so we're going to initialize it here, and we're controlling what it's going to look like. And so if we think of that memory, and memory is actually linear. I mean, by address, it's thought of, you can think of it as a sequence of values, and each byte has an address. So the memory is laid out in a linear way, you know, conceptually. Well, in hardware it's different. But the array, this two-dimensional array, sort of gives the illusion that it's laid out in a table format. But actually, the underlying memory is addressable as a sequence of addressable bytes. So we flatten A, and then we want to see what, you know, what's going on there. So we'll print V at that point. Say we're going to bring that print V function back in there. Let's just, so we're going to print a vector of int. So you should be able to do this pretty easily. You know, how to write a function that prints the values of a vector. So you just have to create a loop that ranges across the indices for the vector. So you start at 0, and you go to v.size, and you quit at v.size, because that's not a valid index. And we'll do cout v of I. And then we'll put a space there so the numbers are spread out. Let's see. We got it. Look at that. 19,999. Okay. And let's put it into a file. That's called a redirection operator. Instead of standard out going to the console, we're going to send standard out to a file named T. You see, we didn't get any printing on the console because it went to T instead of to the console. And we can look at T, and look at, there it is. There's the 1, the 2, and you know, there's no breaks, right? So if I go down to this is the first line. If I go down to the second line, there is no second line, so I can't even get there. So I don't know how to, oh, I know how to do it. I'll press Control, Shift A. I made a second line, and that didn't work. Anyway, there it is. I'm at the end of the line. Oh, that's right. It's caret goes to the front of the line. $sign. I'm in VI. You know, it's an ancient program. $sign gives me to the end of the line. So this is one line. This is a line that's enormous, right? Normally, in the word processor, you know, you have a line which is 80 characters, 120 characters. But this line here, is that many characters long. That's a big line. And that's what it is. You know, a line has a line in a file has what's called a white space, an end line character. So if I go into insert mode here and I hit enter, see, now I've got that line and then I have another line. I'm just going to review this in case you don't know it. See, this is a line, and there's a hidden character right there. You can't see it. It's got a value of 10, which is a new line character. So it's called a white space. You don't see it, but it's hidden in there. So the text editor that I'm using breaks, when it displays the characters, it breaks the line there for us. Does everybody know this stuff? This is like stuff, you know, when I was young, when computers were first invented, and You know, this is like common knowledge, but I don't know if people
I've
think
done
about it
multiple
anymore.
DOS problems since like
Huh?
the 90s.
What?
I've been DOS problems since the late 90s.
Yeah. But like, what's in a character file? You know, you learn that kind of stuff. I mean, I guess I'm supposed to be teaching it, right? I mean, is this news to people or not?
Yes.
Yeah. Okay. So yeah, you know, there's these. What's displayed on the monitor is just an interpretation of memory. You know, the values, numbers that are in memory. And one of the things that and these word processors like VI or gedit, they read these numbers and then display them to you as characters. So that's there's something called a character encoding, or not encoding, a character set. And a character set is an association between numerical values and characters. And so this is what VI is showing us as the characters that the numbers are representing. Now, if we change this is a special character set. If we changed it, if we tell VI this is a different character set, well, this is Chinese. You know, I think they go Big Five. That's one of the. There's several different character sets to represent Chinese. One of them is called Big Five. I think that's what it's called. Any Chinese people verify that? And then we would see Chinese characters with the same numbers in the file. But there would be inconsistencies as well, because maybe some of the numbers are invalid for that character set or produce funny results. So anyway, that's, I don't know if you need to know that stuff. And anyway, that's what's going on. So we did it. That's Flatten. And once again, you should know how to write this print function. Right, that's pretty straightforward, how to print all the values in a vector. And then here is the flatten function. And I have given this on exams in the past, more than one time, this particular problem. I'm not saying I'll give it again, but this is the kind of problem that you have to know how to solve, you know, on the fly in an exam without your notes. So you have to practice these. You just copy the solutions from somewhere else and submit those as your work. That's okay for a grade on the lab, but it's not good for preparation for the exam. You need to practice deriving this code without looking at your notes. And because that's what you'll need to do in the exam. And if you graduate and interview for a job as a programmer, you might very well be given these kind of problems in your interview. And go ahead, write a function that flattens a two-dimensional array. And sit down with a piece of paper and a pencil. And you have to write it out. So you got to know how to do this. And when you're working and solving these problems, you know, this is the kind of thing. This is a trivial problem. Flat. I mean, it's absolutely trivial for anybody who has had some programming experience. So it's a you know, it's not that it's silly to, you know, I have to memorize this. Well, nobody memorizes this. It's just such an easy problem that if you can't do this as an easy problem, then you can't write programs and you can't work at this company, because we need people to write programs. It's like that sort of thing. And not everybody in here is going to be a programmer. I know that. I realize that. But for those who will be, this is the expectation. This kind of problem should be so easy that you just do it. And it's not a matter of, oh, I remember how to do that. No, it's just like, oh, it's obvious how to do that, because you've practiced it so many times. It's like in math. You know, when you do algebra problems and you have an equation, you have to solve for an unknown. You have a variable and you need to manipulate the equation and you solve it. So the variable must be x must be 6. It's so easy because you've practiced it over and over again. and you could pass an exam. You know, you didn't memorize that particular problem resulted in x equaling 6. Just like that, this is a problem that you don't need to memorize. It should be based on having practiced similar problems. The solution should be pretty evident, should come to your mind very quickly. So that's where you need to be at. All right. Should I go on to binary search, or do you want to look at some more problems here? Binary search?
Yes.
Okay. All right, binary search. So let's take a look at that. So here's a function, and let me do binary search using arrays, because I will ask you to write the code for binary search on the exam. I will ask that, and you might want to memorize that. You can come up with it in the exam, but it's a little tough. There's not a lot of code to memorize, but it's like the very beginning of working with more advanced algorithms that are more than a simple linear processing, like Flatten. Okay, so let's go ahead and do that one. So I'll make a directory called binary. And let's go ahead and get rid of that. Oops. We're going to print OK. That says OK. All right, now binary search. What it is, think of these examples I can come up with are so irrelevant these days. You know, think of looking up a phone number in a phone book. I mean, when's the last? Has anyone ever done that?
Yes.
You have.
Yes.
Anybody else? Is there anyone in here who has never used a telephone book to look up a phone number? That's you know, old guys like me don't realize that, you know. And I think last year I was assuming that all the students looked up a phone number in the telephone book. How about a dictionary? You know, how many people use an actual physical dictionary to look up a word? Yeah, you sort of know, right? So how do you find the word? You use binary search, okay? You take it in the middle. You know, I'm looking up a word, you know, like door, you know, and I split it open. Oh, I'm in the M's. Now, does D come before M or after M? Well, it comes before M. And so I'll sort of set aside the right-hand part of the phone book, of the dictionary that I have open, and I'll use the first clump of pages, and I'll split that in half, see? And I'll say, what do I have there? Well, it's a G, right? And I want to find a D. So is D before or after G? Well, it's before G. Okay, so I'm going to use that. Now my sliver of pages that I'm holding on to is getting smaller. And then you split that in half and you get a C. And I say, well, I'm looking for D. Is it D, you know, bigger than C, or, you know, is it after C or before C? Oh, it's after C, so now I got to go to the right. So you zero in on the page. And then, of course, you do, at that point, you may do a linear search, or you may jump around as well in the same way. Whereas you have to use additional letters too, of course. So that's called binary search. And it turns out that in computing problems, binary search is just an underlying problem. It's very common, and it's used all the time. So in binary search, you have to have data that's organized in order. So either the numbers are decreasing or they're increasing, but they can't just be random. If the dictionary just had words at random in it, and you wanted to look up door, it might be on the last page or the first page or the middle page. You wouldn't know where it was. So you would have to do what's called linear search. You check all the words on page 1, and you're looking for door. And then you look at all the words on page 2, and you do that until you hit the word. If the words are not in an order, then you cannot use efficient binary search. You must use inefficient linear search. So when we talk about doing binary search, there's an underlying assumption that the data has an order. It's organized according to some ordering. And let's see, we're going to do the following thing. Let's create some test data. We'll use an int array, A, and we'll initialize it as follows. -4, -1, 0, 2, 5, 12, 99. So there are some numbers. How many do we have? 1, 2, 3, 4, 5, 6, 7 numbers. And so we want a function called binary search. We're going to pass in A. And when we use arrays, we have to give the size of the array. Because unlike vectors, an array is not a class. So there's not any extra information stored about the array, such as its size. It's just a block of memory. So we have A, which is a reference or a pointer or variable that represents the data, the 7 elements, and then there's the information that there's 7 elements in the array. A is actually a pointer in the memory. It points to the first integer in memory. And your code needs to know, well, how many integers are there? You can get me to A can get me to the first element, but I don't know how many you got there. So that's why we have to use that as a second argument. Once again, with vectors, you don't need to do that. And so we want to search for a value. Say we want to look for the number 1. No, not the number 1. Say the number 20. And let's suppose we want the position of that number. We want to know where 20 is. Oh no, not 20. That's not in there, right? 12. Sorry, 12. Where is 12 in the array? Well, it's in, what position is it in? It's in, let's see, that's 0, 1, 2, 3, 4, 5. It's in the 5th, it's in position 5, which is the 6th position. So we want to assert that the position is 5. So this binary search function, the way you were envisioning it, returns the position of some value, 12 in this case, inside the array. So we're going to write this assertion, we're going to test it here. Let's write another test. I don't need to declare position twice. I'm just going to reuse it. So I'm going to delete int there. This position is already declared up here. But we're going to call binary search this time. I'm going to call it with 20. Now, the rule is, the convention is that when you're asked for the index of some value in a sequence and the value is not there, then return -1. Because -1 is an invalid position number. 0 is valid, 1 is valid, all the way up to very large integers. Those are all valid. But positions cannot be negative. And so the convention is, well, let's use is this the largest negative number or the smallest negative number? Would you call that largest negative number or smallest negative number?
It's the largest negative number.
It's the negative number that's the closest to the positive numbers.
Yes.
How's that? Everyone's in agreement about that. All right. So anyway, that is the convention. So these are the two tests. Now let's see. Let's go ahead and write. Let's write the code. Binary search is a function that returns a position value. So it's going to return an int. And it takes an array of integers and a size, call it n, and a value that we're looking for, k. And it returns something. So I'm going to put a stub in there. I'm going to return 0. Maybe n is not good. So I put size in there. Is that better? Size of a. K is the number we're looking for. So this will fail right away. So this search will fail right away. Let's see that. Oh, undeclared. Need the header. All right, so we have a stub. We got it compiling and running with the stub, and our test code is failing. All right. So we got that set up. In fact, I'm going to return a -1 here because that's when we don't find it. Just to remember that -1 means we didn't find it. Let's suppose we didn't find it. So it still compiles. It still fails in the same spot. All right. So now let's try to put into code what we understand based on that example we went through just a moment ago about looking up a word in a dictionary. So what we have is we have to look at ranges, the range of positions. And we're going to keep we'll start with a full range where the start point is 0 and the end point E is size -1. See that? So S is start of the range and E is the end of the range. And we'll start with a full range. All the values are in there. All right, so once again, S is the start position of the range. E is the end position of the range. And we're going to keep cutting the range in half each time. And we'll have a loop. And we'll think about what condition that's going to be in a minute. So we'll need to loop. And inside the loop, what we're going to do is we're going to compute a midpoint. What's the midpoint between S and E? Well, we don't know. I'll tell you right now, S and E are changing. Because initially they start at the 0 and size -1. And then, but inside the loop, we have to think about at an arbitrary point in time, after so many iterations, S is going to be bigger than 0, probably, and E is going to be smaller than size -1, probably. We're going to be squeezing these two bookends, squeezing these two endpoints till they zoom in on the value, or else find nothing there. So S is is not necessarily 0 inside the loop, and E is not necessarily size minus 1. How do you compute the midpoint? Like if S, let's do it like this. And I'm going slow on this because a lot of people don't, it doesn't come to their minds very quickly. Let's suppose that the vector looks like this. I mean the array. These are the positions, okay? These are the positions. Suppose there are 12 elements. So the last index is 11. And let's suppose that S is 2 and E is 7. Now, how do you calculate the midpoint?
E minus S over 2.
E minus S over 2. That's 5 over 2. And 5 over 2, that's integer division. We're going to use integer division. 5 over 2 is 2. So that was a good guess, by the way. So M would be there. That's E minus S over 2. E is 7, and S, look, 7 minus 2 divided by 2. That's what M is. 7 minus 2 over 2 is 5 over 2. 5 over 2 is 2.5, but it's integer division, so it's just 2. So E minus S over 2 doesn't work. Yeah.
Is it S plus E over 2?
S plus E over 2. Let's try S plus E over 2. So it's 7 plus 2 over 2, which is 9 over 2, which is 4.5, which truncates to 4. So in this case, M goes to 4. That's, you know, it's either 4 or 5. There's the exact middle is in between, right? So we got to pick one because this is you know, it's digital, it's discrete, it's not continuous. So we're going to pick 4 instead of 5. So that's the correct calculation. And then look at that. S plus E over 2, that's the average. That's how I think of it. I got S is here, and E is there, and the midpoint is the average. So M is the average, or you can call it the midpoint calculation. So it's S plus E divided by 2 with truncation. Because as we saw up here, there's no exact middle here, right? So there's 4 and 5. The exact middle would be in between here. So we can't deal with that. So we got to pick. We're going to go with truncation and go with 4.
Could E halves work as well?
E half?
E divided by 2. Just eliminating.
I don't think so. S plus E over 2?
Well, eliminating this, just E halves, so half would be 3.5 truncated to 3.
No, and I'll show you why. Watch this. Let's suppose that S were at 6, and E were at 7. Then E over 2 gives us 3.
Yeah, I see.
All right, so we've got the midpoint calculated here. And then we have to ask the question. We've got a midpoint. We're going to look at the middle. See, when you open that dictionary, you don't look on page 1 or the last page. You look at the middle page. Let's look at the midpoint. So if A of M, the midpoint, if what we're looking at there, I'm going to go in the other direction here. we're looking for k. If k is less than what's at the midpoint, if k is less, huh?
Then you reset E to M.
Reset E to M. Yeah, we gotta slide E down. Let's do the problem here. This is seven things. So this is our problem right here. And when we take the average of 6 and S, we get 3, right? So the midpoint goes here. The midpoint is is there. Oh, but we need to. Those are the positions. We have to put our values in there. It's minus 4, minus 1, 0, 2, 5, 12, 99. I'll space them out a little, hard to see. So in our particular example, these are the values. And these are the indices. We start with S at 0 and E at 6. We calculate the midpoint. 6 plus 0 divided by 2 gives us 3. So we're going to look at 3. And we're trying to look for where is k equals 12. Where is 12? So we look at the value at M, it's 3. So k is not less than A of M.
Value of M is 2.
What's that?
The value of A at M is 2. A at 3 is 12.
Oh, sorry, it's 2, not 3.
Yeah.
So then we want to check, we want to compare k. Is k bigger than A of M? K is bigger than, A of M is 2, as you corrected me. And 12 is bigger than 2. And so we want to bring the start position up to M. So in this next iteration, the start position comes to here, and E remains here. And then we start a new midpoint calculation, which will give us this. 6 plus 3 over 2 is 4.5, truncate to 4. And now M is 4, and K, which is 12, is bigger than M. So we've got to bring S up more, again. Bring S up to M. Calculate the new midpoint, which will be 5, exactly, without rounding or truncating. And then we need a condition in here. First we check, is K less than A of M? No. Is K greater than A of M? No. Otherwise, K must be A of M. So K, we found it. Else we found it, right? We found it. We found it at K. Now, binary search, we need to return the position where we found K. So we're gonna return K at this point, and we exit the loop when we do that. See? Let's look at another one. Let's take the problem where we have where we're looking for 20. So when we're looking for 20, we start with S at 0 and E at 6. Midpoint is 3. 20 is bigger than 2 because 2 is at 3. 20 is bigger than 2. And so we set the start point to M. And we compute a new midpoint here, which is 4. And we compare 20 to 5. 20 is bigger than 5. So we move S to M, like we did when we're searching for 12. And we compute the new midpoint here. Now we compare 20 to 12. 20 is bigger than 12. And so we set S to M. We leave E alone, and we compute the midpoint.
So it's gonna be this.
Midpoint is going to be there, right?
So then you're cycling.
What's that?
So now you're gonna be cycling.
Yeah, we're going to be cycling. So does anyone see how we can break that and fix this problem?
Can you just check it beforehand and see if K is greater than A at M or A at E? Return -1.
Check the endpoint.
Yes. Just check the endpoint before you start everything.
Maybe we could do it that way. What's your suggestion?
I was gonna say, you could change that last return K or whatever to if K equals A of M, return M, and then have another else, so if everything else fails, then you break the loop.
If K equals A of M?
Yeah,
No, that's not going to work because this else here see, this will never be reached because these capture all possibilities. If either K is less than A of M or K is greater than A of M or K equals it, there's no other case. K would have to be an imaginary number or something, right? Which is not. Do you see that? So this isn't going to work. See, once we know that K is not less than A of M, and K is not greater than A of M, it must follow, logically, therefore, that K is A of M. So those are the only 3 cases. There's not 4 cases. But I'm going to show you the secret. Although we could follow your suggestion, but it's going to lead to messiness. So I'm going to show you what people do in practice. What they do here is instead of setting S to M, because we already know that K is not at M, so we don't need to look at M. So we're going to set S to M plus 1. Because we don't know if K is at M plus 1. We already know that K is not at M. So we don't need to set S there. Let's set S1 past there to a point that we don't know has K or not. And the same with E. When you slide E down, we know that in this case, if K is strictly less than A of M, we know that K is not at M. So let's set E to M minus 1. All right, let's see how that one works. Let's suppose we want to look for 12. So we start with S at 0 and E at 6, and we compute M at 3. And then we compare 12 to 2. So 12 is bigger than 2. So that means we're going to slide S up. Instead of putting S here, we're going to put S there, because we know that 20 is not there. But it might be, 12 is not here rather, but 12 might be here. So we'll leave, that's a better choice for S. And then we have a new midpoint, which is 5. And look, now we check, is K less than A of 5? No, 12 is not less than 12. Well, is K greater than A of 5? No, 12 is not greater than 12. Well, that means 12 equals 12. That means K equals A of M. And so we're going to return 5. So that still works. Actually, it works better. We cut out one iteration of the loop. What about the case when we're looking for 20? Well, we're going to reach the same point here. We're going to compare 20 to 12. 20 is bigger than 12.
So if S equals E.
And that means we're going to set S to M plus 1, right? So S gets set to here, which is the same position as E. So S and E are right on each other. Now here's the trick. We don't know, we didn't look at that position yet. S and E are equal to the same thing. We didn't look at that position yet. Let's go ahead and look at that position now. So is K less than, well, M, by the way, M is equal to S and E both, right? It's equal to 6. So is K less than A of M? Let's go slowly here. This is M. A of M is 99, and K is 20. Is K less than 99? Yeah. So then we set E to M minus 1. And so E is set to here. And then S remains there. Now that's backwards, right?
If S is bigger than
Now, at this point, we've looked at everything.
Yeah.
We let a tie happen. We let S and E tie for the same position. And then we looked there. And our code ended up modifying E to make E less than S. But if we were looking at 102, then we would have done the other thing. We would have placed S beyond E, okay? So if it's a miss, on one side, E gets smaller than S. On the other side, S gets bigger than E. But at that point, when E and S cross each other like that, there's nothing else to look at. So we exit the loop and return minus 1. But how do we exit the loop? We got to use the loop condition. What's the loop condition?
S is less than or equal to E.
What's that?
S is less than or equal to E.
S less than or equal to E. Yeah, it's okay for S and E to be the same thing. But it's not okay for S to be less than E. Or E to be greater than S. And that's it. That's the most compact form of binary search that I've ever seen. And we could actually follow your suggestion and done extra work. And it just adds
it would've
more
been
logic.
messier.
It's a little messier, so I didn't want to go in that direction. It takes enough effort to get here. Oh, but let's check our test code, right? Let's test it. So this position should be 5. This position should be minus 1. Let's see if that works. Oh. This was a suggestion we looked at. That was something we needed to remove and didn't remove. Here's the test. Assertion failed. What happened? Oh my gosh, look at that. The test failed. I can't believe it. Position equals 5. It's line 35. This fails. What is going on?
You're returning K, not M.
Huh?
You return K, not
Yeah,
M.
look at that. We're returning K. What are we supposed to return? M. Yeah, that's great. See, isn't it good that I didn't practice my lectures beforehand? And then we all participate in debugging together. All right. I mean, as it is, I make it seem artificially easy, right? I mean, to come up with this, you would have on your own a really clean version of this. I mean, how long would that take you? A day? 8 hours? An hour? If you're really smart. I know for me, okay, I'm not a genius. You know, I'm not a genius professor like one of you guys. This would probably take me all day. Well, me now, I mean, yeah, I would get to it faster than that, but back in the day, it might take me more than a day. Anyway, let's get some more test cases going here. And I'm going to tighten this up a little bit. Watch this. Assert binary search A712 equals 5. So I just want to tighten this up a little so we're going to put these assertions all in one line. All right, so we should probably do a more thorough test here. Let's look at a really exhaustive test. Would look something like this. We're going to search for a number less than -4. So say -77. That should be -1. And then we're going to look at -4. We're going to find -4 exactly, and that should be 0, right? So this is an exhaustive test. So -4 is at 0, and -3, that's a value between -4 and -1. That should be -1. And then -1 should be at 1. And then a value between -1 and 0, well, we don't have that, so we can't test that. So we'll take that one out. But 0, if we're looking for 0, that's at position 0, 1, 2. That's at position 2. And then a value between 0 and 2 would be 1, and that will return a -1 because it's not in there. And then the value 2 is going to be at position 3. And then if we're looking for a value between 2 and 5, say 4, that's a -1. And then we look for 5, that should be a 4. And then greater than 5 and less than 12, say a 9, that should be a -1. And then 12, it should be at position 5. And then a value larger than 12 and less than 99, we tried it already, 20. And then we're going to look for 99. That's the last position, 6. And finally, a value bigger than 99, say 120, that should be -1. So that is a pretty good test of this particular array. And we might also want to test an array that has an even number of values to make sure that, you know, the calculations work with an even valued number. Yeah.
Where did it happen that we were required that we had to have like an ordered array?
The binary search doesn't work unless it's ordered. Because imagine, because we're looking at the low, we compute the midpoint. See, let's suppose the midpoint is there. We have to know the value we're looking for. Is it in the left side or is it in the right side? If it's not ordered, then we can't conclude that the value is to the left side. Like if we're looking for -3, okay? And let's suppose that m is right there. Well, -3 is less than 2. So if it's not ordered, then -3 might be to the right of 2.
So will it fail then, right when you say binary search? That's just not going to happen. It's not ordered.
No. We might get it. We might get it just by luck.
So it will try.
The algorithm won't work. The algorithm is based on the assumption that they're in ordering.
So it's just
We would have to write very good test code to make it fail. Yeah. Not very good. I think it would be pretty easy to make it fail. Yeah, just imagine a dictionary where the words are all scrambled up and you cut it in the middle and say, well, I'm on Q and I'm looking for, door. And so I'll go to the left, but actually door's to the right. And then you start moving around and then you're locked into the wrong range forever. And then you say, oh, I didn't find it. Then you return -1, but wait a minute, it was to the right of Q. You see what I mean? It just won't work. Anyway, this is the test code. And just to tidy this up a little bit, did I get this right? Do I have any mistakes in there? Because, it's a real hassle when you have bugs in your test code. And then you don't know if the bug is in your test code or whether it's in your main program. So -4 is at 0, -1 is at 1, and 0 is at 2, 2 is at 3, 5 is at 4, 12 is at 5, 99 is at 6, and everything else is a -1. There we go. I mean, that's not bad. I'm pretty confident at this point we got it right. All right, that's it. Now you have to do this problem not with arrays, but with the vector. Okay, it's the same algorithm. It's just a slightly bit different. You don't have to pass size because you pull it out of the vector itself.